Risk determination, assessment management, identifying and controlling potential uncertainties effectively. Foundations of risk determination, purpose and core risk concept. Risk determination, assessment, and management form a structured decision-making framework used to understand, prioritize, and control risks associated with equipment, processes, and operations. The primary purpose of this approach is to systematically combine engineering knowledge, operational experience, and consequence evaluation into a single, defensible basis for action. At its core, risk is defined as the combination of the probability of failure, POF, and the consequence of failure, COF, commonly expressed through the simple but powerful equation, risk equals POF times COF. While the equation itself appears straightforward, the rigor lies in how each component is determined, validated, and interpreted. Probability of failure represents the likelihood that a piece of equipment or system will fail due to credible damage mechanisms such as corrosion, fatigue, cracking, or operational upsets. Consequence of failure, on the other hand, captures the potential outcomes if that failure occurs, including impacts to safety, health, environment, production, and financial performance. The purpose of combining these two dimensions is not merely to calculate a numerical value, but to enable informed prioritization. By understanding which assets pose the greatest risk, organizations can allocate inspection, maintenance, and mitigation resources more effectively. This approach supports the development of a risk management plan, RMP, which defines actions required to reduce risk to acceptable or tolerable levels. Importantly, risk determination also establishes a common language across engineering, operations, maintenance, and management teams. It allows technical findings to be communicated in a way that supports business decisions, regulatory compliance, and long-term asset integrity. Ultimately, the foundation of risk determination is about balancing safety, reliability, and cost, ensuring that risks are understood, visible, and actively managed rather than reactively addressed. Probability of failure, consequence escalation, and event trees. Assessing risk accurately requires a clear understanding of how failures occur and how their consequences unfold. Probability of failure is not simply a single number, it reflects the likelihood of specific failure modes associated with credible damage mechanisms. Different mechanisms, such as uniform corrosion, localized pitting, or brittle fracture, lead to different modes of failure, ranging from small leaks to catastrophic ruptures. Each failure mode has a distinct probability profile and must be evaluated accordingly. Once a failure occurs, the final consequence is rarely immediate. Instead, it is often the result of a chain of escalating events. These may include the failure or success of safeguards such as isolation systems, alarms, and shutdowns, the behavior of the released material in terms of dispersion, dilution, or accumulation, and the presence or absence of ignition sources or mitigation actions. Because of this complexity, the probability of a specific consequence is typically lower than the probability of the initiating failure event. Event tree analysis is a widely used method to model these escalation pathways. An event tree starts with an initiating event, such as a leak or rupture, and then branches through successive conditional events that either prevent or allow escalation. Each branch represents a realistic scenario, ending in a defined consequence such as a fire, toxic release, environmental impact, or minor contained leak. By assigning probabilities to each branch, assessors can estimate the likelihood of specific outcomes rather than assuming worst-case consequences for every failure. This approach reduces excessive conservatism and improves the credibility of the assessment. It also highlights the importance of safeguards and operational responses in reducing overall risk. Understanding both the initiating probabilities and the escalation pathways ensures that risk assessments reflect real-world behavior and support proportionate, effective risk management decisions. Risk acceptance criteria and inspection planning. Risk assessment becomes truly valuable when its results are used to guide decisions, particularly around risk acceptance and inspection planning. Risk acceptance refers to determining whether a calculated or ranked risk level is tolerable based on corporate, regulatory, and societal criteria. Organizations typically define risk acceptance thresholds that reflect their values, legal obligations, and business objectives. These criteria often distinguish between different types of risk, recognizing that tolerance for environmental or financial risk may differ from tolerance for safety and health risks. Cost-benefit analysis is frequently used to support these decisions, helping organizations evaluate whether the cost of additional mitigation is justified by the reduction in risk achieved. Once risks are assessed and categorized, they play a central role in inspection and maintenance planning. Risk-based inspection, RBI, integrates probability of failure, which is largely influenced by engineering, inspection, and maintenance factors, with consequence of failure, which is often driven by operational and process considerations. This integration allows organizations to answer critical planning questions: what equipment should be inspected, where inspections should be focused, which techniques should be used, how much coverage is required, and when inspections should occur. High-risk equipment is prioritized for more frequent or more detailed inspection, while low-risk items may justify extended intervals. Additionally, understanding how risk changes over time enables dynamic planning, ensuring that inspection intervals remain aligned with actual risk profiles. By aligning inspection resources with risk, organizations can improve safety and reliability while optimizing costs, avoiding both overinspection and unacceptable exposure to failure. Improving risk quality and communication, sensitivity analysis, assumptions, and risk presentation. The quality of a risk assessment depends not only on methodology but also on the accuracy of inputs, the transparency of assumptions, and the clarity of communication. Sensitivity analysis is a critical tool used to identify which input variables have the greatest influence on calculated risk. By systematically varying inputs such as corrosion rates, inspection effectiveness, or consequence parameters, assessors can determine where improved data will most effectively reduce uncertainty. This process helps focus data collection and analysis efforts on variables that truly matter, rather than expending resources on factors with minimal impact. Assumptions are often unavoidable, particularly when data are limited or uncertain. However, overly conservative assumptions can significantly inflate risk values, leading to misinformed decisions, inefficient use of resources, and loss of credibility. Therefore, assumptions should be clearly documented, agreed upon by the assessment team, and periodically reviewed as better information becomes available. Once risks are determined, effective presentation is essential. Risk matrices are commonly used in qualitative and semi-quantitative assessments to visually communicate relative risk using categorized probability and consequence scales. They allow stakeholders to quickly identify high-risk areas without focusing on numerical detail. For quantitative assessments, risk plots provide a more precise view, often using logarithmic scales and displaying risk thresholds or ISO risk lines. Both tools support prioritization, screening, and communication, ensuring that technical results are understandable and actionable for decision-makers at all levels of the organization. Risk thresholds, ALARP, and keys to success. After risks have been assessed and presented, they must be managed through clearly defined thresholds and actions. Risk thresholds divide assessed risks into acceptable, tolerable, and unacceptable regions, guiding decisions on whether mitigation is required. These thresholds are influenced by corporate policies, regulatory requirements, and practical constraints such as available technology and cost. In many cases, especially for higher-risk equipment, the goal is to reduce risk to a level that is as low as reasonably practicable, ALARP. This principle recognizes that while eliminating all risk is impossible, reasonable measures should be taken to reduce risk unless the cost is grossly disproportionate to the benefit gained. Effective risk determination and management rely on several key success factors. These include ensuring that any software or tools used have transparent, documented calculations, clearly identifying specific consequences for each credible failure, and rigorously defining assumptions and uncertainties. Accurate use of POF and COF data is essential, as is understanding what is truly driving risk, whether probability, consequence, or both. Equally important is clear communication of risk results to stakeholders and timely implementation of appropriate management actions. When these elements are in place, risk determination becomes a powerful, trusted process that supports safe, reliable, and economically sound operation of assets over their entire life cycle.